All right, everyone. So, welcome to week 6. And so, while we wait for more people to come in, please look at the fun problem of the day. All right, I'll start going over the problem now. So, three-digit numbers are made up of three distinct digits. And so, clearly, you can just think of this as arranging three distinct digits into three slots. And so, let's look at this from the first digit, then the second, then the third. So for the first digit, there's 9 choices because they can be anywhere from 1, 2, 3, all the way to 9. This is because the digits are 0 through 9, but you can't have 0 as a first digit because this has 3-digit numbers. And now for the second digit, there's 9 possibilities again. And this time it's because it's 0, 1, 2, 3, all the way to 9, except for the one that was chosen as the first digit. And then for the third digit, you can have anywhere from 0, 1, 2, 3, etc. to 9, except for these 2 digits. And that leaves a total of 8 possible choices. And so the answer is 9 ways to choose the first digit times 9 ways to choose the second digit times 8 ways to choose the third digit, which is 81 times 8, and that equals 648. So are there any questions? Alright, so all of you did a good job on the homework, so there's no need to go over the homework this week. And so we're just going to move straight on to our topic for week 6, which is counting and probability. So this week we're going to cover basic counting, permutations, combinations, and the principle of inclusion and exclusion, also known as PIE for short. So first, we're basically going to define some notation. So this is read as the sum from k equals 1 to n of x of k. And it's written this way, and it's basically a shorthand for this. And so the other notation we're going to introduce today is the product. So this is read as the product from k equals 1 to n of x of k. And it's written this way, and is shorthand for this. It's also could be more clear than this. For example, you might not be sure what x1 times x squared all the way to times x to the 8th is. It could be like x to the 1 times x to the 2 times x to the 3 times x to the 4 times x to the 5th times x to the 6th times x to the 7th times x to the 8th. Or it could be x to the 1 times x squared times x to the 4th times x to the 8th. You don't really know, but if you use this notation, you will know. All right, and so here's your first example for basic counting. All right, so I'll start going over the problem now. So a dessert chef prepares the dessert for every day of the week starting from Sunday. So basically, he prepares a dessert 7 times in a week. And each day, it's either cake, pie, ice cream, or pudding. So there's four possibilities every day. And no two desserts can be served 2 days in a row. And on the dessert on Friday is guaranteed to be cake because the problem gives it to you. And so you want to find how many possible dessert menus there are. So let's just look at it like this. This is a dessert for Sunday, Monday, Tuesday, Wednesday, Thursday, Friday, and Saturday. And I'll abbreviate these as the desserts as C E I P. Where this is cake, pie, ice cream, and pudding. And so the dessert on Friday has to be cake. And now for this slot, you can either have E, I, or P. And that gives three possibilities. And the same holds true here, because the dessert on this day does not affect any of these days. So there's three possibilities here. And then the number of desserts that you can have here is only affected by the dessert that's here. And so there's three possibilities again. And you can work forward like this, and it's all three. And so the answer is 3 to the 6, which is 729. And for the people who got 972, I'm guessing that how you got that was probably like 4 times 3 times 3 times 3 times 3 times 3. And this is wrong because it overcounts. Like you don't necessarily know that this slot will necessarily be 3. Sometimes it could be 2. All right, if not, I'll be moving on. So here's a second example. So a short hint for this problem is to try casework on the locate on if the parent rabbits are given to different stores or if they're given to the same store. All right, so I'll start going over this problem. So I said, okay, so the rabbits, Peter and Pauline, have three offspring. So there's two parents and three kids. And they're going to be given to four different pet stores, such that no store gets both a parent and a child. It's not required that every store gets a rabbit. So it's possible for a store to get no rabbits. And so in how many ways can the rabbits be distributed? So as I said earlier, you can casework off of if the parents are in the same store or in different stores. So if they're in the same store, there's four ways to choose the store. And for each of the three remaining kid rabbits, there's 4 minus 1, which is three ways to choose which store they're in. And the kids don't have any restrictions to be distributed among those three stores. So it's simply just 4 minus 1 cubed. And this is equal to 108. And now case 2. So the parents are not in the same store. And since you can tell the difference between the parents, there's 4 times 3 ways to choose which stores the parents are in. And then there's 4 minus 2 stores that can accept any of the offspring. And so you cube this because there's 3 offspring. And so this adds up to 96. And so the answer is 108 plus 96, which is 204. So are there any questions? If not, let's move on. So now we're going to introduce complementary counting. So sometimes it's easier to take an indirect pathway. And instead of counting what you want, count the total number of ways and then count what you don't want. and subtract that from the total. And sometimes it's much easier to do this instead of actually counting what you want. And then other times it's easier to break up what you're counting into smaller and more easily manageable cases. And then when you're done with all of those, you can just combine them, whether it's multiplication, addition, or sum in between. And so overcounting is basically when your count exceeds what the actual count is, and undercounting is the exact reverse. When your count is underneath that of what you should have gotten. And so here's an example that uses basic counting. And it also has to do with overcounting.
I got one.
All right. So I'll start going over this problem now. So handshakes only occur between the people within the group of people who know no one. Okay, sorry. Okay, so at a gathering of 30 people, 20 people all know each other, and 10 people don't know anyone. And so people who know each other hug, and people who don't know each other shake hands. And so you want to find how many handshakes there are. So handshakes occur between the people who don't know no one and with the people who don't know anyone, or between this group and this group. And so the number of handshakes between people who all know each other and the people who know no one is just 20 times 10. And this is equal to 200. And now the number of handshakes among the people who know no one is just 9 times 10 over 2. And this is because there's 10 ways to choose a person, and then 9 ways to choose someone else to shake hands with, but this overcounts by a factor of 2, so you strategically divide it by 2, and so this equals 204, and so this equals 45. And so the number of handshakes that occur is 200 plus 45 equals 245. So are there any questions? All right, if not, I'm gonna move on. So permutation. So an example of a permutation where repetition is allowed is 6, 6, 6, 6, 6. Another one would be 6, 1, 5, 2, 4, 3, 4. And so an example of permutations with no repetition is the top 3 runners in a race. And this is because you can't really tie in a race. And so permutations with repetition. And these are really easy to calculate. So if there's n different types of a thing, then you have n choices each time. And so in general, when you're choosing R of things with n different types, then you have n times n times n times n R times. And so that equals n to the R. And then permutations with no repetitions are what are more normally known as permutations. And so this is a good example of what a problem involving permutations would be like. And so there's 16 choices for the first ball, 15 for the second, 14 for the third, etc. And this is 16 factorial. And so in general, n factorial for integer n is just n times n minus 1 all the way to 1. And if you just want to choose some of them, like 3 of them, you just include the first 3 terms of this. And this is a general formula where there's n things to choose from and where you end up choosing R of them with no repetitions. And order matters. All right, so here's your first example. Alright, so I'll start going over this problem now. It's a bit tricky. So in total, there's 13 times 7, or 91. So suppose that there are 7 boys and 13 girls, and they want to line up in a row. And so when you consider all possible permutations of the 20 people, how many total number of places are there where there's a boy and a girl standing next to each other? And for example, in this permutation, there are 12 places. All right. So in total, there are 7 times 13, which is 91 possible boy-girl pairs. So for each pair, there are 19 places to put the pair, and then 2 ways to permutate the pair. And so this pair also appears in all 18 factorial possible other arrangements of the other people. For example, like look at this pair. Say this is okay. The third, say there's like E1 and G1. And then so there's 19 ways to place them and 2 ways to order them. And then there's 18 factorial ways to place the other people. And so the answer is 91 times 19 times 2 times 18 factorial. And you can simplify this to 91 times 2 times 19 factorial, or 182 times 19 factorial. So are there any questions? All right, so I'll move on then. So here's your second exercise. And by the way, the answer for this question, you should find it to be in the form n factorial divided by 2 to the power of k, where k and n are integers. If you don't, I guess you can, if you somehow find the answer in some other form, if it's equivalent, it's fine. Alright, so I'll start going over this problem now. So a spider has one sock and one shoe for each of its 8 legs. So in total, it has 8 socks and 8 shoes. And so on each leg, the spider must put on the sock before the shoe. And so you want to find in how many orders can the spider put on its socks and shoes. All right, so we're going to strategically overcount here. So in total, there are 16 factorial ways to put on the 8 socks and 8 shoes, because you can tell the difference between each one. And by symmetry, for each of its 8 legs, say 1, 2, 3, and 4 on the left, and on the right, 1, 2, 3, and 4. So it's for each of its 8 legs. For example, take this one. In exactly 1/2 of the possibilities, the sock is put on before the shoe, and in the other half, the shoe is put on before the sock. And the same holds true for this leg, this leg, this leg, this leg, and all of the rest. And so in 1/2 to the 8th of these possibilities, the socks are put on before the shoes. And so the answer is just 16 factorial divided by 2 to the 8th. All right, so are there any questions? All right, if not, let's move on to the next topic. So combinations. So combinations are where order doesn't matter. And when repetition is allowed, one such example is given here, 5, 5, 5, 10, 10. And no repetition is stuff like lottery numbers. Like this is a possible lottery number. And so the general so combinations are important enough that they're given their own well-known way to write them, and it's just like this. And it's read as, when it's written like this, it's read as n choose k. And so the algebraic formula for it is simply r plus n minus 1 factorial divided by r factorial times n minus 1 factorial. And the n choose k form, it's n factorial divided by k factorial times n minus k factorial. All right. And order doesn't matter here. And you're choosing R objects of n. So an example is choosing 3 out of 16 pool balls. And so something interesting to see is this. Oops. Okay. N choose R equals N choose N minus R. And so this is because algebraically these two are symmetric. And so here's your first example. All right, so I'll start going over this problem now. So Pat wants to pick 6 cookies from a tray, and this tray contains chocolate chip, oatmeal, and peanut butter cookies. And so there are at least 6 of each of these kinds. And basically, it's saying that Pat is, and so if you're given this, it's effectively saying you can choose any number of cookies that you want. And so you want to find how many different assortments of 6 cookies can be chosen. So let there be C chocolate chip cookies, O oatmeal cookies, and P peanut butter cookies. And so this is the number of cookies that he's picked. And so you know that C plus O plus P equals 6. And so from here, you can think of these 6 cookies as like 6 circles or whatever. And you can think of these 2 bars as dividers. And so in total, there's 8 choose 2 ways to pick where the 2 dividers can go. And if once you pick the 2 dividers, the rest of the balls there's only one way to order the rest of the balls. And so this is 28. And so for these dividers, they work by all the balls to the left represent the number of chocolate chip cookies. All the balls between them represent how many oatmeal cookies there are, and the balls to the right represent how many peanut butter cookies there are. And this is a one-to-one correspondence, basically meaning that it's unique. Each of these corresponds to a unique combination of chocolate chip, oatmeal, and peanut butter cookies, and vice versa. And so the answer is 28. And by the way, for people who don't know what this method is, you can search it up in more detail later, and it's known as stars and bars. All right, and we're a bit time pressed, so I'll skip this problem. So, principle of inclusion exclusion, also known as PIE. So, the two-set PIE. For sets A and B, the union of the side of the union of A and B is the side of A plus the side of B minus the side of the intersection of A and B. Basically, if like A is, what's the bad color? Basically, let A be 1, 2, 3, and 4, and let B be 2, 4, 6, and 8. Then the union of A and B is 1, 2, 3, 4, 6, 8. And the intersection of A and B is 2 and 4. Yeah. And then 3-case PIE is A is just this. And for 4-case, the pattern just continues. And so on. And so here's an example that uses PIE. So I'll start going over this problem now. So in a room, 2/5 of the people have gloves and 3/4 have hats. And so you want to find the minimum number of people that have a hat and a glove. So really the number of people in the room must be a multiple of the LCN of the denominators of this and this. And that's the LCM of 4 and 5, which is 20. So the minimum number of people in the room is 20. And if you make it larger, you just make the number of people wearing both a hat and a glove larger. And so you can assume that there's no one in the room who neither has a hat nor has a glove. And the reason is because if there were someone who doesn't have a hat or a glove, then all you're doing is increasing the intersection of these two sets. And so that just increases the number of people in the room who have both a hat and a glove. And so from here, you have that 20 times 2/5, which is 8 people are wearing gloves, and 3/4 times 20 equals 15 people are wearing hats. And then here you can apply PIE, or principle of inclusion exclusion. And so you get that 8 plus 15 minus x equals 23 minus x, and this equals 20. And so you have that the minimum possible of x is 3. So are there any questions? All right. If not, that's it for today's class. And thank you for coming. And the handout and homework will be, and the recording will be uploaded soon. Bye.
Thank you.